So let's look at the proof of Lagrange multipliers. Let's go over the theorem again. Suppose f and g are functions of two variables. I should mention in our book, they do this in terms of three variables, but you really can extend this concept to really any size, any number of variables. So we're going to stick to basically 3D pictures and or surfaces, and then smash it down into the xy plane. Okay, so f and g are functions of two variables, so they have continuous first partials, and the gradient of g does not equal the zero vector in a region R in the xy plane, because that's where it would be defined, right? So if f has an extremum at x naught, y naught, so that'll be basically our point p naught, I'll define later as x naught, y naught, subject to the constraint g of xy equal to 0. Now, originally I put in a constant, which doesn't really change the theorem because you do the gradient anyway when you look at the result. But I'm going to change it to 0 for the proof. What we say is it's without loss of generality, meaning it still works for any case if this was a C. But for now, I'm going to leave it as 0 because it works a little better in our proof. Okay, so then you get your multiplier. Then there exists a lambda, so it's a scalar, such that the gradient of f is equal to lambda times the gradient of g, assuming that f of x naught, y naught is an extrema. So in other words, it's parallel to g. And then we looked how to, in the corollary, how to actually use it. Okay, so let's look at the proof. So first, the first part's just the hypothesis. So basically restating the hypothesis. Assume f and g are functions of two variables with continuous first partials, and gradient g is non-zero, etc. Okay, so now we're going to suppose and let f of x naught, y naught be an extremum subject to g of x, y equal to 0. So it is an extremum. Now we're going to show this. So this is basically constructing the curve and defining the curve in terms of a one parameter and then looking at the results to get the gradient. This stuff, appropriate result. So here we go. Excuse me. Okay. So, so the function g of x, so the function g of xy equal to 0 is a curve in the xy plane. And can be parameterized in this way. Can be parameterized by, so basically, I'll erase this, but you have some curve, g, and that's like, f of x, that's like y equals x squared, right? Well, you can parameterize it to make it like a function of one variable, so it like traces it out. So that's kind of what we're doing there. Okay, so it can be parameterized by x equal to h of t and y equal to k of t we will use. All right, and then we'll say that's true for some interval t in I. Then for that curve, we're going to let r of t, so make it a vector valued function, be h of ti plus k of tj. Okay, so we'll let that be a position function for the point that's being traced around. So for the point P of xy, so some value on the curve, we're just supposing that's your xy, and then it's a position function for that point. Okay, so that's your r of t. Okay, so it's being traced out like we normally would think. So here's your position function, and it's tracing this out along the curve, just like that. I'll have to erase. I'm going to erase that in a second. So that's true on the curve C. And then we're going to let P naught of x naught y naught be an extremum or extreme value for f. So it's attained, right? We're assuming that's attained, right? So we're just saying, well, it's going to be at basically t naught, is what we will say. So when t is equal to t naught, some value. So r of t naught is equal to x naught I plus y naught j is equal to h of t naught I plus k of t naught j. So far we're really just constructing kind of what we need to do the result of it. Now we're going to define a function. So now define capital F as a function of one variable, t. We're going to do that by stating f of t to equal f of h of t, k of t. So it like traces out the whole surface basically by, and essentially t varies, but then h and k vary separately. So it might like trace the whole thing out kind of thing. H of t and k of t are on the constraint by our construction there. And k of t are on the constraint. Or x, in other words, xy is restricted to the curve C in the xy plane. Okay, since f of x naught, y naught is an extremum of f, little f of t naught, which is equal to f of h of t naught, k of t naught, is an extremum of capital F of t. So it's just kind of constructing what we need so that we get this result. So if capital F of t naught is an extremum, because, right, I mean, basically we said f has an extremum x naught, y naught. And we're defining x naught and y naught to be h of t naught and k of t naught on the curve. Okay, so that's what we're assuming. So then f prime of t naught must be an extrema. In other words, f prime, and since these are continuous first partials, f prime has to be 0. So what we're getting is that this f of t naught is an extremum. So what we have is f prime of t naught must equal 0. Well, you can see what's going to happen next. If that's equal to 0, we take the derivative of this, and we have to use chain rule. So you get, that's an if and only if we have partial fx of h prime of t naught, right? It's a dh dt thing, plus partial fy of k prime of t naught equals 0, which if you basically factor that, that's the gradient of f of xy dot r prime's derivative, r prime of t naught equal to 0. So in other words, what we have is gradient of f and r prime of t naught, right, at that critical value are orthogonal. By definition, right, 0. But we already know, from earlier that the gradient of g of x naught, y naught is perpendicular to r prime of t. Right, so you have your function, right, being traced out. So your r of t traces out this curve. So that's r of t. R prime is something like this. This is the function g of xy equal to 0. And so we already know that the gradient is didn't do that. Gradient is perpendicular. So gradient of g is perpendicular to r prime. So oops, did that again. So we basically just showed that f, the gradient of f, is in the same direction. So it's lambda times the gradient of f. So it could be like that. It could be shorter, of course. It could be the opposite direction. Lambda could be negative. Okay, it doesn't really matter there. All right, so what that means then is, so thus, I'll just use another transition, thus gradient of f and gradient of g are parallel at that critical value, x naught, y naught. So parallel means that they're scalar multiples. So therefore, gradient of f of x naught, y naught is equal to a scalar, lambda, they choose lambda, times the gradient of x naught, y naught. Gradient of g of x naught, y naught. So that's why you get that lambda in there. So basically, you have those curves, right? You have all these different curves, and you have, did it again. You have your gradient vector that's perpendicular to all of those, and then these are your primes. So F and G are, so if you, this is your prime, well, here, these are your primes, and your gradients are all pointing in the same direction because they're perpendicular. So you have your gradient of G, right, which we've looked at that. Gradient of G is perpendicular to this, but basically we're just showing now that F is parallel to it. So it's lambda times that. Because they're orthogonal. So as long as it's really this right here, they're orthogonal. And we already know that you could, instead of the R here, you put in the gradient of G instead. Still the same thing. Okay, so that's why it works. It's kind of, you still got to be careful how you use it, because you may or may not actually get extrema, but it basically, if there's extrema, that's what you get. So it's kind of one of those concepts. Okay, let's continue, and we will look at one more example. Let's see. We'll just come up to here. So we'll do one more example of Lagrange multipliers. So find the extrema. And usually I will say by using Lagrange multipliers. You know, not something you normally just go do. F of xy is equal to x squared plus 2y squared. Although I have seen many cases where I just said find extrema, and many students went ahead and used Lagrange multipliers, and it worked out real nicely. So it just kind of depends. All right, so find the extrema of f of xy equal to that on the circle x squared plus y squared equal to 1. So this should be pretty straightforward of what we should get. I mean, basically this is a paraboloid, but it's kind of an oblong one, right? It's not circular if you do a cross section. And then that's a circle. So you shouldn't get all points equal. It should be kind of well, yeah, kind of like that. So it should get kind of max and mins, because it's not going to be a symmetric looking thing in all dimensions. All right, let's see. All right, so so this is by Lagrange multipliers. All right, so here's your solutions. We're going to let g of xy equal x squared plus y squared equal to 1. Okay, then we're going to calculate our gradient. So we'll do our gradient of f equal to lambda times the gradient of g. Okay, so do that calculation and you get 2x and 4y equal to lambda times 2x and 2y. All right, so then we have set the components equal. 2x equal to lambda 2x. Simplify that, and you get x times 1 minus lambda equal to 0. All right. And so you get x equal to 0 or lambda equal to 1. Okay, and then next you get 4y equal to lambda 2y. And I basically reduced it out so you have a simpler case to look at. I did a couple steps. You get y is equal to 0. So you get y times 2 minus lambda equals 0. So y is equal to 0 or lambda is equal to 2. And then you have the constraint x squared plus y squared is equal to 1. Okay. So let's see here. If we let x equal 0, then you get 0 squared plus y squared is equal to 1, or y is equal to plus or minus 1. If we let y equal to 0, see, these are independent. Like if x is 0, y doesn't have to be 0. These are totally independent equations. If y is 0, you get x squared plus 0 squared equal to 1. So y is equal to plus or minus 1. So let's see, what about lambda? So does lambda help us at all? If lambda is 1, doesn't help us. We get, so if lambda is 1, you get y times 2 minus 1, y is equal to 0. So that doesn't really help us. If lambda is equal to 2, you get 0 equals 0, or you get x equal to 0. So you get x times 1 minus 2, and x is equal to basically negative x equal to 0. So x, so that doesn't really, these don't really help us. So you throw them out if they don't work. Basically, you use them if they work, and if they don't, you can throw them out. So you use them and then discard them. So we have 4 different possibilities. So let's look at our points. F of 0, 1, f of 0, negative 1, f of 1, 0, f of negative 1, 0. So you do your calculations, you get 2, 2, 1, and 1. So these will be your maximums, and this will be your minimums. That's it. So they are extrema, and you have to just verify which ones they are. So if you get other points and they're in between 2 and 1, you get like 0.5, then you just throw it out. It's not extrema. Okay, one more example. I'll set it up and then you can solve it. So if f of x, y, z is equal to 4x squared plus y squared plus 5z squared, find the point on the plane (2x plus 3y plus 4z equal to 12), where f has a least value. So like f of xyz is a minimum. So you still do, so I'll set it up for you. You still do the gradient of f equal to lambda times the gradient of g. Okay, so move this down a little bit. So this is your g, and then the minus 12 is not going to matter. And this, so you do those gradients and do your setup, and you should get, so you can pause and try this now. You should get 5/11ths. Y is 30/11ths. And z is 8/11ths. Okay, so it's not like a distance. It's just a minimum value. So you have all these points in space, x, y, z, restricted to the plane. Then you want this to be minimum. That's restricted to the plane. So kind of a classic way to do this is you do Lagrange multipliers, because it automatically puts in your constraint. Okay, so check that, see if it makes sense. And I have it worked out somewhere, but okay. I think that's pretty much it for chapter 14, going on to chapter 15 next.